Now, so good. Now, but sometimes we have a circuit like this. How do I find the pole of this circuit? So if I go through this process, first of all, it's a pretty troublesome already. It has two paths, right? One is I can go through CF, another is go through the transistor. I don't know how to do it. But even this is resolved. The CF is not connected, does not have at least one terminal connected to the ground. Right? Just saying that I have an elevator which can only bring me from the third floor to the second floor. So can I treat it as the capacitor that can bring me to the ground? Right? You cannot, right? Because I need to then take the stair from second floor to the third floor. Yeah, something like that. So, we can just ignore it if you don't need to take the exam. Yes. So no, so we cannot use it and we cannot ignore it, right? And then of course the smart people, like someone called Miller, they came up with something. Of course they have some very rigorous proof, but as an engineer, right? This is a good skill. You should ask yourself, well, the only thing stopping me is that this elevator only stops at the second floor. Can I model it as two elevator or equivalent circuit that it can bring me to the ground, right? So the analogy is not too good now, but the question is this: can I transform this circuit to something like this? Now the rest should be the same so that I still have the major function of this circuit. But I'm not claiming this circuit is still going to work. I'm just saying that can I transform it to a circuit from which I can find a pole that is equivalent to the pole that I have in the original circuit. I only care about the pole, but the function of the circuit will be different. I basically saying that can I do this? Can I split the capacitor? Yes, exactly. Like this. CF1, CF2. Right? So basically I'm saying that can I transform this circuit to this and find the pole? Now obviously this circuit and this circuit are not the same, right? Do not say I try to split it and then I have the right circuit. They are not the same. They don't have the same gain, maybe, probably. They don't have the same function. But however, their pole, I want them to be the same. I want they have the same pole. So I will use this by transforming this from this to here to find out the pole, and then I claim that this two pole equals to the pole of these two circuits. Okay, so that is the purpose, and that is called the Miller capacitor. So let's try to prove it using the so-called Miller theorem. Now, in order to do this, we also need to be aware of that. This capacitor has some special connection. It connects to a port here and the other terminal to another port. And there's some relationship between the voltage across this port. They are not independent, right? For example, if this is V1, if I ignore the capacitor, this one is like a gain times V1. Okay, if I ignore the capacitor, which is just the gain of a common source amplifier. They have some relationship. Okay, so we assume that we have an impedance with two ports. Okay, and and they are related by V2 equal to A times V1. So how do we transform the circuit? So it is like this. I have an impedance, which is CF. This is impedance, not capacitor, okay? For capacitor, it needs to be 1 over C, right? We will see that later. Okay, and I have two ports. I have one, I have two, okay? So my goal is that if I apply current to here, it will be I1, and then apply V1. And then here I have I2, right? Just notation, current always go in, right? You just make it negative, you need it, and this is V2, right? So what is the relationship, right? How do I say it? Now, I should say that this one, I want to transform to another circuit. Like this. That is our goal. And I call this CF1, CF2. And still this is V in, V1, I1. This is still I2, V2. So basically, I'm saying I have this resistor. I apply V1 and V2 on the left and right. Then I will get current 1 and current 2, right? If I transform it to this circuit, as long as it gives me I1 when I apply V1 on the left and give me I2 when I apply V2 on the right, they are equivalent to the rest of the circuit because I see the same thing. There's the same effect, right? This is like the analogy I told you earlier. Like I push this table, I feel that this table is heavy, right? It may be someone is pushing against me. It doesn't matter. Because to model my effort, I can just say that I have a very heavy table that I'm pushing and no one is pushing against me or helping me. Make sense? So the goal is that what should I put for CF1 and CF2 so that I get the same current and voltage ratio, right? So let's start by looking on the left. What are the Ohm's law? V1 minus V2 divided by CF equals to I1, correct? Ohm's law. That's it, okay? But I also know that V2 equal to A times V1 divided by CF. I mean, V2 equal to A times V1, right? Is this okay? So because of this, I can factorize it. I have I1 equals to V1 times 1 minus A divided by CF. So V1 divided by I1 equals to CF divided by 1 minus A. Okay? Okay? So then what do I get? I find a relationship between V1 and I1. So I just need to set CF1 equals to CF divided by 1 minus A. I'm done. Right? It's just like basically someone is pushing against me, but now I will just say, no one is pushing against me. I just make the weight of the table to be its real weight divided by 1 minus A. Then that is what I'm feeling. Right, so all I'm doing here is use Ohm's law to find the relationship between V1 and I1. Ohm's law is always correct. V1 minus V2 divided by CF equal to I1. This is Ohm's law. This is the physics. But now I just say I don't care about V2. I just want to say I apply V1, how much current I will get. Then I find that it is equivalent to modeling as CF divided by 1 minus A. We will do that, yeah. Is this okay? Now, then someone say, how about for CF2? Right. So let's try that. We don't know. We have V2 minus V, maybe I just put I2 in the front will be better. I2 by Ohm's law again is V2 minus V1 divided by CF. But what is V1 in terms of V2? Is V2 divided by A, right? And you just use the same thing, you will get V2 divided by I2 equals to ZF divided by 1 minus 1 over A instead of 1 minus A. Huh? And because of this, all I need to do is just set CF2 equals to CF over 1 minus A. 1 over 1 minus 1 over A. Okay, so basically here I show you that, wow, if you have an impedance connected to two ports and the voltage has some relationship among these two ports, V2 equal to A times V1. You need this relationship for this theorem. Then I can just cut it into two independent circuits with the first resistor divided by 1 minus A. The second resistor divided by 1 minus 1 over A. Then they are equivalent to the external investigator or whatever, right? This summarizes what we just said. I have a pot, I apply left V1, right V2, and it is equivalent to, I just break them, so CF becomes Z1 or Z2, and they are connected to ground with one terminal connected to ground. They are still connected to port 1, let's you cut it, but you need to transform Z1 to be ZF divided by 1 minus A, and Z2 equal to ZF divided by 1 minus 1 over A. Okay. Now this one is something very important. What we have discussing is the impedance, not resistance. Not a capacitance, right? And we know that the impedance of a capacitance equal to 1 over omega C. So it's going to be opposite, right? So if I have a capacitor, like what we discussed earlier, CF, from the port 1 to port 2, right? The impedance equals to 1 over CF. So I'm going to cut it, transform it into two independent systems like this, which is okay. But however, what I require is ZF1 equals to ZF divided by 1 minus A. That's what we proved earlier, right? But that means what? Is 1 over CF times 1 minus A. So it means I actually need to put a CF times 1 minus A instead of CF divided by 1 minus A. So you need to be careful about this, right? For inductor, then it's the same. For resistor, it is the same. But for capacitor, because of this reciprocal relationship, right? You assume this are larger than 1. You will feel that I need to reduce the impedance by certain value. I reduce it, right? But for capacitor, you need to increase it because so that its impedance can be reduced. Larger capacitor, smaller impedance. Make sense? Right? So similarly, now someone talking about negative, I will show you later. Yeah, you feel that that's negative, right? But we won't. CF2, again, based on our study earlier, it needs to be what? Equal to ZF divided by 1 minus 1 over A, right? But ZF is CF 1 minus 1 over A, right? So you need to put a capacitor here with 1 minus 1 over A. So be very careful, right? In exam, I give you an inductor. Then you need to do the right thing. Any questions? No, I never asked you to derive. No, why you don't need to derive? Think about this. I already showed you a general impedance. And inductor is omega L. Then it's the same, just like resistor, right? It's just this one I want to spend some time to make it clear to you. Don't make the mistake by reducing the capacitance. Okay. Now, then what does it mean? It's good to have some, let me see how many more slides. Simulation also. I just want to, again, right, I always say many times, but as an engineer, you should have this feeling that very often is like how you feel, like the weather is that it's 72 Fahrenheit, but you always tell you feel like 74. But it's 72, why you keep saying that feel like, right? What is the observatory doing? It's because of humidity, you make it feel like or whatever. It's just like this, I push the table, it's heavy, right? This table is, let's say, 20 kg. I feel it is heavy, heavier than 20 kg. Maybe the floor is very rough, or maybe someone is acting against me. I cannot see it, right? I feel like it is 30 kg. And same here. Now, I want to say this one. I have two ports. One is input, one is output. And I have this, now F stands for feedback. You probably understand now. It's a feedback capacitor. We have not learned it yet, but it's connecting the input to the output. We have this capacitor. So as an electron, as a voltage, you look into this capacitor, what capacitance do you see? It turns out it is not CF, because we try to do what we did earlier. We try to do the Miller theorem. We break it into CF times 1 plus A0 and CF times 1 plus 1 over A0. Now you may ask why now you become plus, because the gain is negative this time. Okay? Here we have A equals to negative A0. So I'm doing 1 minus negative A0. So that's why it's 1 plus A0. That's why you won't get negative capacitance in this case in our class, because we always have a negative gain to make the system stable. Okay? And you are giving me CF, but what do I see? It feels like it's a very large capacitor. What is the problem? You make me very slow. Yeah. I spent so much effort to develop a new technology that has a small capacitor in the input. Let's say the transistor CGD. I waste a lot of money to develop. And then you hook up the circuit in a way there's a feedback. And although I give you only 1 femtofarad, every time I apply a pulse, I feel like it is 1 picofarad. Then I'm very slow, right? 1 femto can bring me maybe to terahertz, and I always stuck with 1 gigahertz or 100 megahertz. Yeah, so that is what happened here. And can we understand intuitively why this happened from electrical circuit? The reason is because we only care about the pulse we apply. From Ohm's law, this is still CF. Physics is still CF, but I only care about the the pulse I apply, right? So at the input, I apply, for example, delta V, right? Then my question is, how much charge I need to give to this capacitor in order to get delta V, okay? But the Ohm's law tell us that CF, or the physics tell us that the charge is equals to delta Q divided by, now I should not say delta V, divided by V in minus V out, right? Because it's the difference of here, right? The change of V in minus V out. I actually should say the change of V in of V in minus V out. But what is V out? I already say V out is V in times negative A. Right? Basically saying that I increase the voltage from the input, this guy will just drag the voltage down further. Right? If the other side is 1, I increase the voltage, then I charge this current. But whenever I increase 1 millivolt, the other side will try to reduce by 10 millivolt. That causes a problem that I need to apply more charge. Because here, it tells me this is equals to delta Q divided by delta V in times 1 plus A. Okay? So it means that the charge I need to put equals to delta V in, let me just call this delta V in, times CF times 1 plus A. So I am the one only putting delta V in. If your capacitor is CF, then I only need to put delta V in times CF. But because of this feedback, I put in delta V in, I actually need to put delta V in times CF times 1 plus A. That isn't for me I feel it is a very large capacitor. Now, or think in another way. Think about what is a capacitor? It's just like a reservoir. I put in the water, and then the level will go up. Now, if you have a large reservoir, very wide, I need to put a lot of water to let the water rise, right? If it's a small reservoir, then I don't need to put very little amount of water, then the level will rise, right? Now, what it's doing is like this. Whenever I put in some water, the bottom of the reservoir will keep sinking. So I put this amount, it does not rise so much because the bottom keeps sinking. And then for me, I feel that, wow, this reservoir is really huge capacity, a big capacitor. I need to put a lot of water into the reservoir in order to raise the potential by that amount. That is basically what's happening, right? So try to think in this way, right? But physics is still correct. It's just because the bottom is sinking. Of course, I do need to put so much water in order to raise it by this amount, right? Okay, good. So if this is the case, we can try to solve this circuit, right? How do we solve it? The first thing is to break it. I'm going to break this one into two capacitors, CF1, and this becomes CF2. And then it will be easy. We just follow what we have learned before. Look at the path. And how many nodes do we have? We have 2 nodes. Yeah. And then the first node is, this time I'm going to be quick, right? R. I forgot to ground, right? All the independent source. R equals to, for 1 is RS, right? Because if I stand here, I see RS bringing me to the ground. This side is the gate, infinity, right? And then the C equal to CF1. But what is CF1? Times 1 minus A, okay? Where A equals to V2 divided by V1, okay? So I have this one, then you find the pole is 1 over RS 1 minus A times CF. Do you see this? A small CF, I have a very large denominator. Then you have a very low frequency. Your 3 dB gain going to be very early. And that's the problem of the so-called Miller effect. You will learn this in digital circuit. I only have a very small capacitor between the gate and the drain. Later you learn it CGD is small, but because of Miller effect, it slows down your transistor. Okay? How about the second pole? R equals to RD, right? Again, I assume no channel length modulation. Otherwise, it's going to parallel R0. And then what is the C? CF2, which equals to CF times 1 minus 1 over A, okay? But what is A? That is the question, okay? So the A, of course, to be accurate, it should be the A at the frequency you're interested in. But if I know the A at the frequency that I'm interested in, then why I need this approximation method? I already have the transfer function, right? So we are going to take the A right before the frequency you're interested in without the capacitor. So when you do the, do I say it here? The gain is assumed to be constant without capacitor, okay? So now if you don't have the capacitor, what is the gain of this transistor, of this circuit? What type of amplifier is this? Negative GM RD. That's it. Now, so you see that 1 minus A equals to 1 plus GM RD, which is positive. So you will get an increase by about maybe 10, right? So maybe next time I'll do simulation. It just time's up. Okay, thank you.